Let's keep going through the study guide. We'll start now on section 1.2. If you are just coming off of the last video, you're going to be in roughly the right place already. If not, you can go to the contents of the book and click on 1.2 and it'll get you right to where we need to be. This video is not going to be as long as the first one. That one involved a lot of explaining about the philosophy of the study guides and how to fill out the different types of questions and what types of answers are acceptable and not acceptable. This one, I am not going to be quite as detailed about that. I'm also not going to fill in as many of the definitions. I'll point you in the right direction to find them within the textbook. I'll clarify things that I know might be a little bit trickier to understand, but ultimately this should not be another hour-long adventure in filling out a study guide. If you do need more support after you get done watching the video, just set up a quick meeting with me or show up at the student hours tomorrow between 2:30 and 3:30 in my Zoom room. There's information about those and about scheduling meetings with me in the syllabus, and I am genuinely more than happy to clarify anything that I might have glossed over in the process of making this video. So we start with looking at the difference between qualitative data and quantitative data. I am going to point out something interesting, though, in the chapter. It does mention that lowercase letters like X or Y are used to represent data values. Data coming from a population or from a sample. So just put that in the back of your brain for a little bit, because we're going to notice something as the book goes on about the use of lowercase and uppercase letters in the formulas that we'll get and the methods that we get for analyzing things. So you don't have to write anything down, but just notice, sometimes things are lowercase, sometimes things are uppercase. I wonder why that might be. We'll get there eventually. So, types of data: qualitative data and quantitative data. Qualitative data, they're saying in this section, is also referred to as categorical data. And it is things that are qualitative qualities. I think of it as qualities or characteristics, and quantitative data as quantities, measurable amounts. And so this will be things like color. It will be things like anytime you've taken a survey that asks you whether or not you're satisfied with something, and it's rated on a scale from, like, sometimes the scale is a numerical scale. It's like from 0 to 5, but 0 doesn't mean the quantity 0. 0 means you're not satisfied, and 5 means you're very satisfied. So like those are called Likert scales, by the way, but for now let's just say like a satisfaction scale. Satisfaction scale. It could be something like agree, disagree. Those are all categories of things. Quantitative data now is things that you can measure. So that's speed, distance, height, weight, literally quantity, like how many, ? Those are all things that can be measured, so measurable things. Quantitative data, always numbers. They are things that we can use to calculate. We can do meaningful things with those numbers. Qualities, we can't do computations. We can't do dissatisfied plus very satisfied. that doesn't make any sense. Like there's no calculation that we can do that makes that type of data make sense. So qualitative data are qualities. Quantitative data is things that are measured in numbers. And over the next 2 sections, we're actually going to break this down into even more categories. So first, they're saying that quantitative data, there are 2 different kinds. There is quantitative discrete data and there is quantitative continuous data. So quantitative discrete data, this is can only be represented by specific values. So if I ask you for the number of people in your family, and we could specify immediate family or whatever, so the number of people in your immediate family, you are going to answer something like 3 or 5 or 9 or some number. You are never going to say 2 2/3 because it doesn't make sense to have 2/3 of a person. If I ask you how many books you checked out from the library last semester, you're not going to say, I checked out 2.5 books, or I checked out 2.3785 books. That's just not the way we talk about books. And so discrete data is the stuff that can only take on a specific value. So like whole number values. It could be that it could only take on specific increments of decimals. So I might say that I am testing how long it takes people to walk a mile to the nearest half minute. And so I could have 1 minute, I could have 1.5 minutes, I could have 2 minutes, I could have 2.5 minutes. Nobody's walking a mile in 2.5 minutes, but I'm still, those are the only numbers that I'll accept because those are the only numbers that I have said are valid for me to talk about it. Continuous data, though, that's stuff that can take on any value. So can take on any value. And so that could be something like height, distance, time, if I'm allowing for decimal measurements on that. Anything that, you know, if I asked you how tall you are, it's not likely that everybody is going to say a specific foot and inch combination. Like there's variations in the height. And if we measure things accurately, we're going to see that you could take on any value. Like at some point in your life, you were pi tall, 3.1415, because at some point you were shorter than that, and at some point you were taller than that. But as you moved through all of the heights, you hit every one of them in between the height you were born at and the height that you're at now at some point. It's a continuous scale. And so that's the difference between continuous and discrete. Is it only specific numbers that work, or could it be any number that works as we're representing things? And so you can see some examples here. It asks about the number of books students have in their backpacks. That's going to be discrete unless you like tore a book in thirds. That's not what's intended by that. So yeah, you've got 5 books in your backpack. You've got 0 books in your backpack. That is discrete data. The data are the number of machines in a gym. You sample 5 gyms. One has 12 machines. One has 15 machines. One has 22 machines. Those are all specific numbers that happen in whole number increments. That's discrete. If we're looking at continuous, that's usually going to have decimals, it's going to have fractions, those types of things. And so this here, those are all continuous numbers. They're not whole number increments or specific increments. Here we've got lawns in square feet, sampling some houses. The areas of the lawns are 144, 160, 190, 180, and 210. That data is discrete. Those are whole number intervals. They're not continuous intervals. Here we've got some things with ounces now, and I see decimals. And when I see decimals like that, if they're not in very specific increments, it's going to be continuous data. So you have the opportunity to try out a few of those. There are some things now about talking about qualitative data, like the way that qualitative data is, they keep track of it. If you were doing something where, also this chapter gets into sort of the types of graphs that we might use to show different types of data. So if you are looking at something like classification of students, that is qualitative, right? That is a quality. It's not a quantity. You've got freshmen, sophomores, juniors, and seniors. You see them all in the pie chart. You know that this all adds up to 100%. Pie charts are a great way to represent a lot of qualitative data because we're not comparing we're not comparing the categories to each other in a measurable way. We're just comparing the number of people in those categories or the number of data points in those categories. Here we see number of credit hours completed per student. This is a graph that shows us that like 250 students have between 10 and 13 credit hours, and 575-ish students have between 13 and 16 credit hours. These are qualitative, right? We could count how many credit hours somebody has. If somebody has 13 credit hours, they've got 6 fewer credit hours than somebody who has 19 credit hours. Those numbers make sense to add and subtract to each other. They're in specific increments. So this to me looks like quantitative because it's talking about quantities. It looks like discrete because you can't have half a credit or a sixth of a credit or any fraction of a credit. These are all whole number values. So that data is quantitative discrete data. If we look at qualitative data here, let's see, what do we have? Tables comparing the number of part-time and full-time students. So part-time versus full-time, those are categories. Those aren't measurable, subtractable, addable quantities. Full-time students, part-time students, they're in categories, and it looks like at this particular institution, there are a much bigger percentage of full-time students than at the other. You can try to make sense of that data, but it might make more sense to do those as pie charts. It seems like having the table there, it gives you a lot of raw data, but to make sense of it, looking at it as a pie chart makes the comparison a little bit easier. You could also do it as a bar graph. Again, the comparison is a little bit easier. The type of graph you choose is going to depend on the type of data you have. So how could you have percentages that add up to more or less than 100? Like here we've got part-time students and full-time students, and if you add those together, you're going to get 100%. If your students are either part-time or full-time, there's no other way for that to happen. But you could have something like full-time students, students who want to transfer, and students under the age of 25. And those categories could have overlap. So these full-time students, some of them might also be in this under age 25 category. So if you try to add up those percents, you're going to get more than 100%. So you can't do a pie chart for more than 100%. That doesn't make sense. So in those cases, it makes sense to do things like bar charts that compare the categories. You could also have a case where it adds up to less than 100%. So if we're looking at these ethnicity breakdowns, the percentages show up here, but it didn't include any data for people who didn't feel like they fit any of these categories or didn't know what category they fit. So there were, let's see, out of 24,382 students, over 2,830, well, exactly 2,838 of them fit this other unknown category. They didn't answer. This is only that representative of those people who answered. So without that category, you're not going to get the full 100%. Again, bar charts probably make sense in this case so that you can make some of those comparisons without complicating things because there's a chunk of information that's missing. Pie charts. Let's see. There's just more examples of charts. Take a peek at those. It is not, it's not overly complicated, but spend some time making sure that those types of things make sense to you. The definition for Pareto chart, that's something that's showing up in our vocabulary list. The Pareto chart is this one that is figure 1.10, and the comparison is between 1.9 and 1.10. 1.9 is just a bar graph, and 1.10 is a Pareto chart, and the difference is you'll notice it's sorted by size, so you should be able to get that definition. I'm just going to write here in these notes, look at the section with graphs and figure 1.10. So see if you can come up with a definition that captures what that Pareto chart actually is. All right, on to, what's a scenario that might cause percentages to add up to more than 100%? We saw one already. See what you can come up with for that as well. On to sampling. Sampling is super, super important. Like we've got to, when we're doing inferential statistics, where we're using information from a sample to predict something about a population, we don't always have access to data for the entire population, so we have to figure out how to get samples that are going to give us the best possible indication of what we're looking for our population data. And so random sampling, it says that random samples are samples where anyone or any, I don't want to say anyone because I don't want to enforce that populations can only be people. So where any, let's see, what does it say here? Any group of individuals, any, well, let's say individuals. So any individual is as likely to be picked as any other. Any individual is as likely to be picked as any other. So that's random. It's hard to do truly random samples. So this is likely to be picked as any other. And that's the that's the simple random sample. Let's see, random number. a simple random sample if any group of individuals is as likely to be picked as any other group of individuals. And so, no, the easiest method to describe is called any group of individuals, any. So this is the same definition as the one above it, except instead of individual, it's group of individuals. And again, write that however it makes sense to you. You don't have to copy what I'm writing. That makes sense to me because I know my own shorthand, but you'll want to make sure that you write it in ways that it is helpful for you to understand. So choosing a simple random sample, they go through the process of doing that. There's information there about it. They talk about using random numbers. You can actually get tables of random numbers. There's even a whole book of random numbers. It's something that I've gotten people kind of as a joke gift before. A book of random numbers. It's kind of famous. I challenged a friend of mine to read that as part of like a live stream at some point, the way people read books, to just sit and read all of the random numbers in the Million Random Digits book. So there are tables for random numbers. You can have random number generators online. We could get into some conversations about what truly is random. I might link a video or two to the class resources, but you can come up with random numbers and use random numbers to help do sampling, and it explains how to do that here. There are some instructions on how to do that in the TI 83 and 84 calculators. As I said when we were talking about the requirements for this course, you don't need those. You can go and ask, go search online for a random number generator and ask it to generate 3 random integers, and it will do that for you. So this can be accomplished in other ways. So another one that we need to look at is the stratified sample. So actually a few we need to look at: stratified, cluster, and systematic samples. So these are all random samples. A random stratified sample is when you divide the population into groups, and those groups are called strata, and take a proportionate number of a proportionate number of individuals from each strata. So this is different from just taking a random selection of individuals from a population. Let me add a page to this so that I can kind of walk through this to show sort of the difference and why a stratified sample might be beneficial. In the last video, I gave an example of wanting to get information about the amount of time that student athletes sleep each night. So if I did a random, just a simple random sample here, student athlete sleep averages. If I did a simple random sample of the student athletes at VTSU, I could end up with let's just say I want to do a simple random sample of 20. I could end up with 3 softball players, 1 lacrosse player, 5 tennis players. Let's see, I've got to get this to add up to 20. 7 basketball players. And let's see, 10, 16, 4 baseball players. And that just was what happened when I randomly picked a bunch of players or a bunch of student athletes. But if I tried to do a stratified sample, so a stratified random sample, stratified random sample, I would look at how many athletes play each sport. And so if I'm gonna make this up because I have no idea what the actual information is, but let's say that there 20% of the athletes at VTSU are baseball players. I don't think that's true, but let's just pretend it is for a while. I would make sure that 20% of my sample came from baseball players. And if 15% of the students are tennis players, I would make sure that 15% of my sample came from the tennis players, so that my sample looks more like the makeup of my population. And if I do it randomly, I don't get that. I don't know why I just erased a whole bunch of stuff there. But if I do this, you choose from each sport the number that makes your sample look most like your population. You still pick those at random, so I still pick 15% of the player, or 15% of my sample I pick randomly from tennis players, but I'm keeping those categories as close to the makeup of the population as possible. So that's the difference between just a simple random sample and a stratified sample. All right, and then we have a cluster sample. So this one is dividing into clusters. These are, let's see, not proportionate. So cluster samples is kind of similar. You still break the sample, or break the population into categories. But choose a random number from each category. So in the case of athletics, now instead of picking a proportion of my sample coming from different sports, I just pick a random number from each of the sports until I have the number of people that I need. And so those are cluster samples. A systematic sample is a way to pick a starting point in your data at random, and then pick your sample by using a specific interval from that sample. So if I have a list of 50 names, I go to my random number generator and it gives me the number 12. So my sample I'm going to do by starting at number 12, and I'm going to take every fourth person in the list. And so I'll take number 12, I'll take number 16, I'll take number I can math. I'll take number 20. I'll take number 24. I'll have a system for picking the next sample based on where I start with the random number. And so that can be kind of useful, although like things like having a list of names that are alphabetized, you could end up with really unbalanced things based on the commonality of the starting letter of a last name. You might only have 3 people in a list of thousands whose last name starts with a Q, and the likelihood of them getting picked in a systemic sample is kind of unlikely because there are so many names that start with other letters, and that can introduce other types of bias. So just from a cultural standpoint, there are certain places in the world where names more commonly start with certain letters. And so you might, if you sample based on the phone book and you get the phone book. We don't have phone books anymore. I've just shown my age there. But if you start with an alphabetized list of names and you start towards the end of the list and you have a lot of people in the list who have traditional Chinese names, you're going to have lots of Y's and lots of Z's as starting letters. And so you might introduce a sort of cultural bias that you didn't expect. You think you're picking at random, but you end up having a sample that is has far more Chinese representation than a sample would have if it were truly randomly generated. So it can work. It can be tricky, but systemic sampling is something people do an awful lot. Convenience sampling, it is not random. So convenience sampling, non-random. That's where you really pick your sample based on what's easiest to you. So you could do a survey of students and you stand outside of the dining hall to ask the students questions. And the convenience sample at that point is those are students that you've got access to. You can stand outside the dining hall and students will walk by, but those students are probably residential students. Those students are probably traditional students. It's not going to be representative of your entire population. So convenience sampling can be tricky. It's non-random, relies on access to the members making up the sample. Okay. And so I'll let you read some more about that. You can see that there are things that are called sampling errors and non-sampling errors and sampling bias. And those are all things that are included in your study guide. You know exactly where they are now. You know how to find them in the text. You can come up with your own definition based on that. And then also we've got some practice question here. So a study is conducted to determine the average daily foot traffic on hiking trails in Vermont during the summer season. Each trail in the following samples is monitored for daily visitor count. What is the type of sampling that's used in each case? And you'll pick from the ones that are offered there. So there's a bunch of different examples. There are also examples in your text that you can use to make sure that you understand the differences. And if you are using these practice problems in the text and having trouble, reach out to me and I will clarify for you. It's a little bit more vocabulary after that. Variation. Variation is really the heart of what we study. So if I'm looking at test scores for my students, it is very rare that everybody gets the exact same score on the test, and it's really uninteresting if everybody gets the exact same score on the test. So looking at how the scores are distributed and how different they are from each other becomes a really useful tool in being able to do statistical analysis. And so you can look at variation and the definitions there to fill in the final piece of the 1.2 section of your study guide. So I promised you less than an hour. I got it down to 35 minutes, and I'm betting the next one's going to be I don't want to make promises I can't keep, but we'll see. I will stop this one now and I'll start a new video for 1.3.